All right, so today we're going to look at the very last section in the book that we'll be talking about today. This is the singular value decomposition. Really, as it turns out, this is one of the most useful applications of linear algebra in real world. In the real world, we'll look at an example of how we can apply this to data compression, to sending images, say, over the internet if we don't have the space to send a high definition image, or if you're YouTube where you don't want to lose your customers, so you need to send a reduced quality version of a movie so that people are not going to click away depending on the bandwidth that they have available. That's really what's going on with the singular value decomposition. And so we'll look at that example, and we'll actually data compress an image and see what happens. But before we get to that, we need to think about what's actually going on in the linear algebra behind the scenes. And the key idea with this is that if A is symmetric, we've talked about how we can come up with an orthogonal diagonalization of A. Right, so we can write A as P, D, P inverse, where D is diagonal and P is an orthogonal matrix. That is orthogonal column vectors, which are unit vectors as well. Right, so, but maybe we have a matrix which is not symmetric. So we're going to look at an image file converted to a matrix. That is, we'll look at an image file that is just a grayscale image where we can look at every single point in the matrix as a measurement of how much gray we got at the corresponding pixel or a corresponding point in our picture. Right? So we'll convert a picture to a grayscale matrix. That is just a matrix of how much gray, how much black versus white we're actually using at a particular point in the picture. Now that matrix that we get is not going to be symmetric. So what if A is not symmetric? That's our problem, right? So what are we going to do? Well, we actually discovered and pointed out that this is true. We have an orthogonal diagonalization only if A is symmetric. So this is not going to be true. We won't be able to do a PDP inverse if I don't have a symmetric matrix. So we're going to have to do something a little bit different. So we have to relax our PDP inverse. What we will find is true is that for any matrix A, we'll be able to write A as U sigma V transpose. Remember that P inverse was P transpose for the symmetric matrix, where this is, it's going to be, I'm going to put diagonal in quotes. It's going to be a diagonal matrix, but it might not be square. So it's going to have a matrix where entries are going down along a diagonal, but it may have some extra zeros at the bottom or some extra zeros on the side because it's not actually going to be a square matrix. But it's as diagonal as possible for a non-square matrix. And these are both orthogonal. Right, so that's what we're going to do. We're going to create a diagonal matrix that has orthogonal matrices on either side, and then we'll see why that's useful and how we can apply that to a data compression question. Now, I'm not going to go through all of the theoretical stuff that's going on behind the scenes here. I'm going to describe for you what we'll do, starting with A, in order to come up with U, sigma, and V. It's a bit complicated. There's a bunch of steps in the process. But I'll describe all of the steps, and then we'll apply that to a couple of examples so that you can see how we're going to come up with this. So the first idea that we need in order to understand what's going on here is that A may not be symmetric, but A transpose times A is, no matter what A is. And the reason that that's true is because, remember, what does it mean to be a symmetric matrix? It means that if I take its transpose, I get the same matrix back. So if I take the transpose of this, remember that if I take the transpose of a product, I transpose each piece, but I have to flip the order. So if I transpose each piece but flip the order, then I'm going to get an A transpose times A transpose transpose. But transpose transpose is just A. So A transpose is A transpose A, which means that A transpose A is itself, which means that it's symmetric. And so that's our first key point. A may not be symmetric, but A transpose A is, no matter what. Which means that I can orthogonally diagonalize A transpose A. Right, so A transpose A has an orthogonal diagonalization. Which means that I can come up with eigenvalues for this matrix and then eigenvectors as well. And in fact, enough of them to make a square matrix full of linearly independent eigenvectors. Right, so this has an orthogonal diagonalization, which means that it has eigenvalues. Let's call them, so this is now square, right, as well. If it's symmetric, it's got to be a square matrix, and this is actually always true. A transpose A has got to be a square matrix. Suppose that A is, let's say that A is m by n. That means that A transpose is n by m, which means that A transpose A is n by m times m by n as far as matrices go. Remember how this works. What we actually get is n by n back. Right, so A transpose A is a square n by n matrix, which means that I'm going to get n eigenvalues, lambda 1 through lambda n, and corresponding eigenvectors v1 through vn in my orthogonal diagonalization. Now, it may be the case that some of these eigenvalues are 0, right? In fact, that's likely. And remember that if I have a matrix which is non-invertible, I'm going to end up getting 0 as at least one of my eigenvalues. And so that's often going to be the case. So in that situation, we're actually going to ignore the non-zero eigenvalues. But so now at this point, let me start writing down our process. So just keep in mind that lambda 1 through lambda n are going to be our eigenvalues for A transpose A. As it turns out, I'm not going to prove this. It's really just a one-line proof. It's in the book if you'd like. These things are, in fact, always bigger than or equal to 0. Just by virtue of the way that we've created. These eigenvalues are, in fact, always positive. So what we're going to do is we're going to put these in decreasing order. So we're going to put these things in decreasing order and only include the non-zero ones. So here's our goal. When I talk about a singular value decomposition. So 1, we start with the matrix A, and then we look at the matrix A transpose A, which is now symmetric. And then we calculate lambda 1 through lambda n, the eigenvalues, and v1 through vn, the eigenvectors. And then we're going to put these in order where lambda 1 is bigger than or equal to lambda 2, is bigger than or equal to lambda 3, is bigger than or equal to lambda n, which we know is bigger than or equal to 0. All of these things are positive, and we're going to put them in decreasing order. And then, so we may have to rearrange our eigenvectors as well, so that the eigenvectors match up with the eigenvalues. This is all via our orthogonal diagonalization process that we've talked about. And that's step 1. And that's a long enough step, right? The orthogonal diagonalization process can be involved by itself, especially for a matrix that's bigger than, say, even 2 by 2. Again, we'll look at some examples of these, but that's the first step. The second step, sigma, our middle matrix, our diagonal, pseudo-diagonal matrix. This is what we're going to do. We're going to create it, but not out of the eigenvalues, but just because of the way everything puts together, we actually have to take the square root of all of the eigenvalues. Right, so here's what we're going to do. We're going to create a matrix. It's got to be the same dimensions as our original matrix A. So the same size as A. So that's the first thing. And then we start up in the upper left-hand corner and we put the square root of our eigenvalues going down along the diagonal. Right? So we're going to put the square root of lambda 1, the square root of lambda 2, all the way down until we run out of non-zero eigenvalues. We're only going to include the zero, the ones that are actually positive, that are not zero. So that might not be all of them. So we're going to call this lambda r. Right? And now, once we get to this point, right, it's possible that if I need this to be the same dimension as the matrix A, I might need to keep on going across, right? So if A had more columns than it did rows, then I'm going to need to keep going across, and I'm just going to put zeros here, right? So it is possible that I'll have zeros going that way to fill everything up once I run out of non-zero eigenvalues. So non-zero eigenvalues. But it's also possible that my original matrix A was longer than it was wide, which means that I may run out by the time I get to this point, and I might need to put zeros down here, right, to fill out the rest of the size. So we're going to get a diagonal matrix in the upper left-hand piece, and then I might have extra zeros this way, or I might have extra zeros going down, depending on the size of the original matrix A. These things in here, the square root of those eigenvalues, are called the singular values. Remember, we're putting these in decreasing size. So lambda 1 through lambda n went down, so these are also going to be going down as well, down in size. All right, that's step 2. We've created our middle matrix sigma. Step 3, we're going to create V. Remember, our whole point is that A is U sigma V transpose. So we've talked about how to get sigma. 3 is how to get V. This is also relatively easy. V is really just going to be the columns V1 through Vn that we got from our orthogonal diagonalization process. But in this case, we're including all of them. So it's a little bit different than before, because this matrix, remember, we only include the non-zero eigenvalues after we square root them. Over here, we're going to include all of them, no matter what. And so we're going to include all of these vectors that we got from our orthogonal diagonalization process, all of the eigenvectors of A transpose A. All right, so these are, so the V1 through Vn are the eigenvectors of A transpose A. And again, they go according to the same order as our decreasing order of the eigenvalues. All right, and finally, we're going to create U. This one is the most complicated. Sometimes it's easy. Sometimes you got to take this extra funny step that we'll see in the examples. Right, so we're going to create U as follows. All right, so we are going to take, let's remember our size here, right? So this is the same as the size of A. So if A was m by n, this is m by n. Remember, V transpose is created out of n different eigenvectors, but they're eigenvectors corresponding to an n by n matrix, A transpose A, which means this is in fact n by n, it's a square matrix, and it'll be orthogonal, which means it's got to be square. U is going to be m by m, so that when we multiply these things together, it makes sense. Right? It makes sense, and in the end, we're going to get an m by n back as well. But if I want to square m by m matrix, where n is the size of this, here's what we're going to actually end up doing. Right? So we're going to start by remembering that we had lambda 1 through lambda n are n different eigenvalues for A transpose A, and then we actually we just looked at lambda 1 through lambda r, not n, the non-zero eigenvalues. Right? So the non-zero eigenvalues. These are the ones that we use to create our diagonal matrix sigma. So then when we then we took these to the square roots, right? So the square root of lambda 1 through the square root of lambda r, which is sigma 1. So this is a new symbol that I'm including here, through sigma sub r. So sigma for singular values. Right? Singular values are the square roots of the eigenvalues of A transpose A. Right, so that's fine. But now we only have r different eigenvalues, the r non-zero eigenvalues. So what we're going to do is look at the eigenvectors v1 through vr that correspond to these non-zero eigenvectors. So now we're not going to look at all n eigenvectors. We're just going to look at v1 through vr. And then we're going to look at AV1 through AVR, but we have to normalize them to make them unit vectors. Right? And this, after we do that, that is our matrix U. So we normalize by dividing by the length. And again, it's a complicated process. There's lots of steps involved in doing these, but actually, we have to be careful. There's one more step here. This is R vectors. We need to make a square matrix that has m columns. So R may not, in fact, actually be enough. We may need to include some more vectors here so that, in fact, I get an m by m matrix. This is tricky to describe here. We're going to see it in examples. But really what we need to do is we need to take these vectors and we need to add some new ones so that we still have an orthogonal basis for Rn. Right? So we extend these first ones by adding some new vectors to get an orthogonal basis for Rn. And again, we're just going to look at some examples to see what exactly I mean by that. It doesn't happen every single time, but sometimes we don't get enough eigenvectors, v1 through vr, so we need to add some new ones in order to make a square matrix that is, in fact, orthogonal. And that's the whole process. And so let's just jump right in to a couple of examples so you can see how it works. All right. So we're going to look at the matrix A, which is 2, 3, 0, 2. And we're going to find a singular value decomposition, SVD. Now, this is not a symmetric matrix, right, because I don't have the same thing if I flip across the diagonal. So I cannot get an orthogonal diagonalization. But our first step, then, is to look at A transpose A. A transpose A is 2, 0 if I go turn column 1 into row 1, and then 3, 2, multiplied by A. And that makes 2 times 2 is 4 plus 0. That makes 6. That makes 6 plus 0 is 6. And that makes 9 plus 4 is 13. So that's A transpose A. Notice that this is in fact symmetric because if I flip along the diagonal, the 6 and the 6 match. And that was our first claim, that A transpose A is always symmetric. And that's true here. So I get a symmetric matrix. Now I'm not going to go through this whole process, but remember what we do next. We find the eigenvalues and eigenvectors. For A transpose A. As it turns out, those eigenvalues are 16 and 1 in decreasing order, and the eigenvectors that we get corresponding to those are 1 over root 5 and 2 over root 5 for the first, and the second one is negative 2 over root 5 and then 1 over root 5. Right, so this is our orthogonal diagonalization process. Remember that we do need unit vectors here. For our orthogonal diagonalization process, we find the eigenvalues, we find the eigenvectors, but then we need to normalize as part of the process. So that's why we had to divide by lengths, and we end up getting square roots in the denominator. But so this is our V1, and this is our V2, corresponding to our given, our values, our eigenvalues for this particular matrix. Now, we could do that. That wouldn't have been that hard here because this is a 2 by 2 matrix, but that's something we've looked at a bunch before, so you'll just have to trust me that, in fact, this is the eigensystem that we get for this particular matrix. All right, which means at this point, we can create our diagonal matrix sigma. So 2 sigma. So what we're going to do is we're going to take the square root of the eigenvalues. So we have singular value 1 is the square root of lambda 1. Singular value 2, which is, in this case, square root of 16, which is 4. Notice that I put these in decreasing order, and notice also that they're both positive. That's always true. The eigenvalues that we'll get for A transpose A will always be positive, so we can always put them in decreasing order. Sigma 2, our second singular value, is the square root of lambda 2, which is the square root of 1, which is 1. Remember that we stop after we've looked at all of the non-zero eigenvalues. This particular matrix didn't give us any zero eigenvalues, so we include them all. We'll look at an example next where we do have to do something a little bit trickier, but for right now, all of our eigenvalues are non-zero, so we include them all. Which means that my matrix sigma is a diagonal matrix that I get by just listing these singular values along the diagonal, which means I've got 0, 0 here. Remember, my original matrix A was 2 by 2, which means sigma also has to be 2 by 2, and I don't have to include anything extra on the side or on the bottom. Again, we'll look at an example where we have to do that, but we don't have to do that here. All right, so sigma is also 2 by 2. All right, so that's good. 3, we create V. Remember that V we get just by lining up every single eigenvector. So V in this case is just V1 through Vn, all of them, regardless of whether they corresponded to eigenvalues of 0 or not. But in this case, there's just 2 of them, and I have to use them all, and I still put them in order from greatest eigenvalue to lowest eigenvalue. So 1 over root 5, 2 over root 5, minus 2 over root 5, 1 over root 5. And that's our V. Okay, so let me just store the stuff that we need here. We have lambda equals 16, So sigma lambda 1 was 16, so sigma 1 was 4, and V1 was 1 over root 5, 2 over root 5. We had lambda 2 was 1, so sigma 1 was the square root of that was 1, and sigma 2, and V2 was our second, minus 2 over root 5, 1 over root 5. So the final step is to create the matrix U. And remember that we get U by looking at A V1, A V2, all the way through A VR, where R is all of our eigenvalues that are not 0, and then we normalize. But these all corresponded to non-zero eigenvalues, so we include them both. But then I have to normalize them. So it's A V1 over the length of A V1, where A was our original starting matrix, and then A V2 over the length of A V2. And there's lots of calculations that go along here. I'm not going to work all of these out on the board. You can just use your calculators to calculate A times V1. Here's V1. We started with our matrix A, 2, 3, 0, 2. You can multiply these together by hand or with your calculator. Then dividing by the length is where it gets a little bit just tedious. But I've worked these out, and what you get when you do that is 2 over the square root of 5, 1 over the square root of 5, minus 1 over the square root of 5, and then 2 over the square root of 5. This is just what you get if you calculate AV1 over its length and AV2 over its length. All right. And again, in general, we need to make a square matrix, which is m by m, where m was the number of rows of my original matrix A. A was 2 by 2, so this is m, and this has to be m by m. So it has to be 2 by 2, which it already is. Again, we'll look at an example where that's not the case and we need to do some extra stuff, but for right now, we're good enough. And so now we've got U. We already created sigma. We already created V. And so now we're done. All right, so now we will check that A is in fact U sigma V transpose. And we'll go over to Mathematica, put all of these things in, just multiply them and see what we get, and notice that it in fact works.
All right, so I have used our Mathematica program to store the matrices that we've calculated, beginning with our matrix A that was the matrix we started with. S is our diagonal matrix sigma that we calculated. We also calculated V, and here we see it, our V and U here. Finally, I asked the program to simply calculate U times S times the transpose of V, and we see that it does in fact return the matrix A, letting us know that our calculations were correct and we have found the correct singular value decomposition for our matrix A.
All right, let's work out another one. This one will have an extra wrinkle involved. Let's start with the matrix A, which is 1, 0, minus 1, 1, 1, 1, and let's find a singular value decomposition as before. So this matrix is not even square. And so this is the first thing. When I say that any matrix has a singular value decomposition, it's any matrix. It doesn't have to be even a square matrix to start. Because when I take A transpose times A, which is 1, 0, minus 1, 1, 1, 1, and then multiplied by 1, 0, minus 1, 1, 1, 1, what we're going to get is, in fact, a square matrix. So this is 3 by 2. So this is 2 by 3. This is 3 by 2. Remember what happens when we multiply. The middle number is gone, and we end up with a 2 by 2. So we get a 2 by 2 square matrix back. 1, 0, and 1 makes 2. 1, 1, 0, and minus 1 makes 0. 1, 0, and minus 1 makes 0. 1, 1, and 1 makes 3. So this is A transpose A, and it's a 2 by 2 matrix, and it is in fact symmetric. We can read off the eigenvalues because it's a diagonal matrix. We can say that lambda 1, remember we go in decreasing order, so lambda 1 is 3, and lambda 2 is 2. Now, this one we can't read off, but if we work out the eigenvectors, I've worked this out, the eigenvectors turn out to be 0, 1, and 1, 0. And these are already normalized because this is a length of 1 and this is a length of 1 as well. Remember, you got to make sure that we get unit vectors and for all of our eigenvectors. So now we're so far in good shape. At this point, I'm in a position to construct the diagonal matrix sigma. So sigma is the singular values, which are the square root of the eigenvalues in decreasing order. Square root of 3, square root of 2. But remember that sigma has to be the same dimensions as A. A was 3 by 2. So sigma has to be 3 by 2, which means that I have to have 3 and 2 across. But I've used up all of my non-zero eigenvalues. If I want to make this 3 by 2, I need to include extra zeros at the bottom. So this is one of the new things that we're seeing here. I have to include these so that sigma is the dimension that I want it to be. Okay, so let's save our information again here. So right now we've got that lambda 1 was 3 with corresponding eigenvector 0, 1. We've got that lambda 2 was 2 with corresponding eigenvector 1, 0. And then we calculated our sigma right here. The next step is to calculate V, but remember that V is just all eigenvectors that correspond to that we get ever, right? So all of them. Again, this one doesn't have any non-zero eigenvalues. We'll look at one more example where that does actually happen. But since this one has since all of our eigenvalues are positive, we use them all when we created sigma. But no matter what, you use all of the eigenvectors when you create V. Right? So V is just going to be our eigenvectors, V1, V2 here, because that's all of them that we got. They're already normalized, so we get 0, 1, 1, 0. Finally, U. U is often the toughest to actually construct. Right, so when I want to construct U, remember what I need to do. Right, so I need, notice that, A was 3 by 2, sigma was 3 by 2, V was 2 by 2. So if I'm looking at U, sigma, V transpose, right? So sigma is the same dimensions as A, which is 3 by 2. V is a square matrix, so the transpose is still 2 by 2. So this product makes sense, and what we're going to get, if I look at the second 2, is the middle goes away, so we're going to get a 3 by 2. The only thing that it makes sense for U to be is 3 by 3, so that I can multiply it by a 3 by 2 matrix. So U has to be the 3 by 3 matrix. Now, here's where we get a little bit of a problem, because remember what I do. I take AV1 divided by its length, I take AV2 divided by its length, but that's it. That's all I got. I only have 2 vectors here. Right? So I only have I only have two vectors. Now, we'll see, we'll work this out. When I take A times B1, because A was in fact 3 by 2, this is going to be a three-dimensional vector. Right? So even though this is just 2, right? So A was 3 by 2, V1 is 2 by 1. So when we multiply, I get a 3 by 1. So this actually has 3 entries in it. This has 3 entries in it, but I need a 3 by 3 matrix, which means I need another vector. Right? I need another vector. I need another column in order to make a 3 by 3 matrix. And I needed you to be an orthogonal matrix. All right, so that's the first thing. As it turns out, these are already going to be orthogonal, so that's good. But the question is what to do with this one. Now, I've worked out all of these things. What we get here, when we actually work them out, is 1 over root 3, 1 over root 3, 1 over root 3, and 1 over root 2, 0, minus 1 over root 2, for this entry and this entry, but I still don't know what to do with this last one because I need a 3 by 3 matrix in order to make this work. And here's how we're going to work this. This is sometimes the trickiest part. Remember what we need. U needs to be an orthogonal matrix, which means it needs to have 3 orthogonal vectors, which are all unit vectors. If you notice, if you dot these together, I get 1 over root 6, 0, minus 1 over root 6. These are already orthogonal. So this vector and this vector, if I take these two, are already orthogonal. Which means all that I need here is another vector which is orthogonal to both of these. Right, so I need this one to be perpendicular to both of those and a unit vector. Now, the simplest way to do that in this particular case is simply to cross these two vectors together. Now, it can be more complicated than that in a larger matrix situation. We're not going to really have to worry about this too much. And this is going to work for us in this case. If I took U1 and U2 and then I cross them together, then I get a vector which is perpendicular. And in fact, since these are unit vectors, the length of the cross product is going to be a unit vector as well. So what I'm going to put in here is U1 cross U2. That will be a vector which is perpendicular to both of the starting ones, which means we actually get a basis for R3 out of that. Now, I've worked this out for you. If you cross these vectors, and you're careful, what you end up getting is minus 1 over root 6, square root of 2 over 3, and minus 1 over root 6 again. Right, so this is what we're going to put in for our third column of the matrix U. And the final thing, now we've calculated, written down sigma, we've written down V. The last step is to, and we've calculated U. Our last step is just to simply check, is A equal to U sigma V transpose? And again, we'll go over to Mathematica and check that. And then we'll come back and look at one final example where we have a matrix that leads us to singular values or to some eigenvalues, some of which are 0. That's the last wrinkle that we have to understand how to deal with.
Okay, similar to last time, I've told Mathematica to store our matrix A, 1, 0, minus 1, 1, 1, 1. I also stored our calculated matrices S, which is our diagonal matrix, and V, the matrix of eigenvectors, and then U, the more complicated matrix that we came up with. Finally, I asked it to calculate again U times S times the transpose of V, and when doing so, we find our original matrix A as we hoped.
Okay, so one last example of these, a final situation that can occur. Let's look at the matrix A, which is minus 3, 6, 6, 1 minus 2 minus 2. So we're starting with A. Again, we look at A transpose A. Just as last time, that will end up, since this is 3 by 2, we'd have a 2 by 3 times a 3 by 2, which is a 2 by 2 matrix. We calculate the eigenvalues of A transpose A. We actually find that lambda 1 is 0, and well, if we go in decreasing order, we get 90 and we get 0. So we get 1 positive eigenvalue and 1 zero eigenvalue. And again, I've worked out our corresponding eigenvectors. The eigenvectors are negative 3 over root 10, one over root 10, 1 over root 10, and 3 over root 10. So that's V1 and V2. Okay, so this situation is different because remember, when we make our diagonal matrix sigma, we only include the positive eigenvalues. So this one is out. However, remember when we make our matrix V, we include all of the eigenvectors. So we will, in fact, make both of these. Right? So sigma is square root of 90. That's the only one that we've got that's positive. We're trying to make a diagonal matrix, but it's got to be a 3 by 2 as before. So square root of 90, there's nothing else to make, so everything is 0. All right, so that's sigma. V we make out of our eigenvectors, V1 and V2. Minus 3 over root 10, 1 over root 10, 1 over root 10, 3 over root 10. Right, so that's V. We include all of those, even though we only had to use our positive ones over here. Now, when we go and we create our matrix U, remember that U is AV1 over its length, AV2 over its length. Now we're in the same situation as the last example that we looked at, where we need to end up with a 3 by 3 matrix because we started with a matrix with 3 rows. We're only going to get 2 out of this, so we need something else to put there as well. Again, I've just calculated AV1 over its length and AV2 over its length, and what, as it turns out, what we end up getting is 1/3 minus 2/3 minus 2/3 and 2/5, 2 over root 5, 0, and 1 over root 5. All right, so we still don't know what goes in our third column, but this is exactly like the previous example that we've looked at. We need to fill this third column out with a vector which is perpendicular to both of these, with a unit vector which is perpendicular to both of these. So if I call this U1 and this U2, well then I'm just going to cross those and put it up in there. And when I cross those, what we end up getting is 2 over 3 root 5, 5 over 3 root 5, and minus 4 over 3 root 5. And this is our matrix U. Now we've got U, we've got sigma, we've got V. So finally, we'll check, is A equal to U sigma V transpose. We'll go back and do that on Mathematica. And then after we do that, I'm going to work through an entire Mathematica project that really does show the data compression application of this. It's not something that you're going to be tested on. It's not something that you'll even have a quiz or a homework question about. So feel free to skip it if you'd like. It's not going to be that long. It'll be about 10 minutes, and it really is quite interesting, where we look at how we can use this process to take a picture and compress it. We lose some quality, but sometimes that's necessary when we're transmitting stuff. So at this point, we're going to move over to Mathematica, and we're not going to come back. And that's the whole course. I had a good time, so hope you did too.
And our last example is similar to the previous. I've got our matrix A. I've got our diagonal matrix S that we calculated, V, and U as well. Finally, when we calculate U times S times the transpose of V, it returns for us the matrix A that we began with. All right, and so to end the semester, we're going to work through this Minitab project, which helps us to understand what's going on in many data compression techniques. So I will make this Minitab file available to you so that you could look through it if you'd like, but I'm just going to talk through what I've done here. You can actually do this. Minitab is pretty nice. Mathematica. Mathematica is pretty nice here. You can actually copy and paste any picture in here, or drag and drop it from any file folder right into the screen. And so this first command, all that it does is convert your picture to a grayscale. So that is, there's no color left in your photograph after we've done this. You could actually do everything we're doing with the color photograph. It's just the files get way bigger, but it's basically the same idea. Now, our next command here, this image data command that I'm using, converts our file into a matrix. And the matrix, it's a big matrix. We'll see how big it is in just a minute, but it's a matrix which contains a bunch of numbers between 0 and 1, which really just tell the ratio of black to white at every dot in the original picture. So we get a big matrix that gives the grayscale information for our photograph. And in fact, the output's so large that Mathematica says it's large output. I don't want to put it on the screen because it would be almost meaningless, it's so large. And we can look at how big it is by using this dimensions command. So it's in fact a 200 by 150 size matrix, and if we multiply those numbers together, we get 30,000. So this picture of this parrot gives us a data file with 30,000 entries when I convert it to a grayscale matrix. All right, so the singular value decomposition, remember, gives three matrices. We called them U, sigma, and V, so that U times sigma times V transpose recovers the original matrix that we started with. Now, we don't have to remember the syntax to be able to reproduce that for Mathematica, but it's pretty straightforward. In this case, it's just singular value decomposition of the data file that we want to create. So this is a matrix, remember. And so again, it gives you a big output. In fact, it gives you three different matrices. What I've done in the next command is recombine those according to, so this is the first matrix when I put this 1 here. This takes our decomposition, the first matrix. This takes the second matrix, and this takes the third matrix. And I'm multiplying them together, but this has been transposed. The third one has been transposed. So I multiply the three matrices together that are found when using the singular value decomposition. And then finally, this command image returns that grayscale matrix to an image. And we see that we recover the picture of the parrot that we started with. And that's simply because when you take the three matrices obtained from the singular value decomposition and multiply them together, U, sigma, V transpose, it recovers the original matrix that you started with. So that's why the picture returns to the picture that we started with. All right, now the whole idea when using singular values to compress a picture is to say, all right, well, maybe I've got a whole bunch of singular values in my singular value decomposition. That is a whole bunch of eigenvalues from A transpose A. But let's just focus on the biggest ones. So let's just focus on some eigenvalues that, say, at the beginning here, what I'm going to do first is just focus on the 5 largest singular values and ignore everything else. So rather than having a matrix that includes all of our singular values for sigma, we're just going to have a matrix that has 5 singular values, which is going to reduce the size of sigma, and then it'll reduce the size of our matrices U and V on the outside as well. So we're going to have a much smaller data file to use because we're only using 5 singular values. Now, if a singular value happens to be small, if it's close to 0, we'll see that it doesn't contribute much to the actual picture. And if we can ignore a bunch of the singular values, we can end up with a matrix that has less than 30,000 entries, but hopefully still looks almost as good as our original picture. All right, so all that I'm doing here is I am, rather than making a singular value decomposition with all of the singular values, I've just told it to restrict to the 5 greatest singular values. And when we do that, we do end up getting 3 matrices. The output, though, is actually not too big. It actually outputs it on the screen for us because it's smaller than before. There's still plenty of numbers, but the output is much smaller. And now what I've done is I've reconstructed the image by using this singular value decomposition using just the 5 singular values. So I've taken the first matrix times the second matrix times the transpose of the third matrix, and then told it to create the image. Now we can sort of see the parrot, the outlines of the parrot in there. It's certainly not a very good picture. We've lost a lot of quality because we've only used 5 singular values. Now, but what does it cost us to do that? Or what do we gain, right? So how much data are we using in order to generate this picture? Well, we can check that out too. We can take the dimensions of each of our matrices in the singular value decomposition using 5 singular values. There's the first dimension, there's the second, and there's the third. So already it's much smaller. If I multiply these together to get the entries in the matrices and then add everything up, we end up with this number, 1775, which is the same as, this is about 6%. So if I took 1775 divided by 30,000, so we get about 6%. So it only takes about 6% of the initial data to recreate this picture. So again, the picture isn't that good, but we've only included 6% of the original data. And so the next question might be, well, what if I include more singular values? Can I get a better picture and still have a reduced load on the data? And so what I move to next is using 50 singular values. This program is set so that you could actually choose whatever you want to put right here. We just call it K. But I put in 50. So we're putting in 50 singular values, and then I've put in a single command that does everything here, right? I just put it all into one line of code. Told it to take the singular value decomposition with K singular values, but K is 50. And then we've got the first matrix in the decomposition, the second, and then the transpose of the third. And then this command image returns that to an image. And this is what we get out of it, right? So we get a picture of a parrot that doesn't look that bad, right? And in fact, if I go back up and look at our original picture, here's our original picture way at the top. You can see a small difference, right? This original picture is better. It is better than the one that we've calculated down here, but nevertheless, there is not that great of a loss of quality. It is a pretty good quality picture. And next we can ask, how much data do we actually take to create this picture? How many entries total are there in our 3 matrices in the singular value decomposition? Again, we can go down and just calculate the dimensions of each of those matrices, multiply them together, add everything up, and in the end we get 20,000, which is 2/3 of the original amount of data, because we had 30,000 entries in the original file. So this picture takes only 2/3 of the data, and most people would agree that it's better than 2/3 of the original photograph. Right, so this is a pretty good quality. It's certainly not only 2/3 of the quality. It's much better than that. And so we actually have gained something out of this process. We get a picture that's not that bad for only 2/3 of the data. And that's the power of the singular value decomposition. Now, as we increase our singular values even more, I could move to 60. and then redo this command. And this is the image. And this one is almost as good as the original picture. However, in doing so, we can ask ourselves, how much data do we actually use? Now we use 24,600 data values. So we had 24,600 while using 60 singular values. And what that in terms of a percentage, that's 41 out of 50 or 82%. So this picture looks almost perfect, but it only costs 82% of the data compared to the original data file that was used. And again, that's the power of the singular value decomposition in terms of data compression. It's not the only use of singular value decomposition. This topic is one of the most widely used applications of linear algebra. And that's where we're going to end our course. Again, hopefully you've had some good times and learned some linear algebra. And look me up again if you need to take an online math course at Oakton Community College.